This video will cover the right-hand rule. In physics, there are two ways of multiplying vectors together. So when you're multiplying a number together, just two scalars, you just use standard multiplication rules. But if you are multiplying two vectors together, two symbols with an arrow above them, there are two different ways that we can do this. One is with the dot product, which is used to calculate a scalar answer. In the dot product, you use a dot symbol between the two vectors, and the way we calculate the dot product from there involves multiplying the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. An example of a dot product would be in the work formula, where work equaled F dot D. Here, the equation simplifies down to the magnitude of F times the magnitude of D times the cosine of the angle between those two vectors. But the cross product is a little bit more complicated. The cross product is a way of multiplying two vectors together such that you get a resultant vector that points perpendicular to the other two vectors. To determine the magnitude of a cross product, the formula is pretty similar to that of the dot product. To calculate the magnitude of a cross product between two vectors, you'll take the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. One example of a cross product is when we're calculating the force acting on a charge that is moving in a magnetic field. The formula is F equals Q V cross B, where V and B are both vectors, so we have to use a cross product there. Another example of a cross product would be the torque, where the torque equaled R cross F. The cross product requires thinking in three dimensions, so most of our problems have only dealt with X and Y. Motion in the left and right direction, that's X, and motion up and down, that's Y. But we actually have a third dimension that we live in, and that's the Z axis. We can either move into or out of the page when we think about motion along the Z axis. And so when we're drawing these vectors that point in the Z direction, we need to use special symbols to indicate their direction, because we're trying to draw this on a two-dimensional surface right here. So we can create a coordinate axis of X and Y just as we always have, but if we want a vector to point out of the page in the positive Z direction, we use this symbol, a circle with a dot in the middle of it. And if a vector points in the negative Z direction into the page, we use this symbol, a circle with an X in it. Another way of thinking about this is using your fingers to curl in a direction. If your fingers of your right hand curl in a counterclockwise direction, your thumb will point out in the positive Z-axis, out of the page. But if you curl your fingers in a clockwise direction, you'll find that your thumb points into the page in the negative Z direction. So we had a formula that we just identified that will calculate the magnitude of a cross product. But if we want to figure out what direction the resultant vector from a cross product is pointing, we need to use the right-hand rule. To use the right-hand rule, first point your index finger in the direction of the first vector. Then curl your middle finger into the direction of the second vector, and if you extend your thumb after that, your thumb should point in the direction of the resultant vector that you get from the cross product. So let's take a look at an example. Let's imagine that we have a proton with positive charge moving with a velocity of 1 meter per second to the left in a uniform magnetic field of strength B equals 1 Tesla in the upward direction. Determine the magnitude and direction of the force acting on the proton from this magnetic field. So the formula for magnetic force is QV cross B. That will get our force from the magnetic field. So first we're going to calculate the magnitude of this magnetic force by using the magnitude formula. That would involve the magnitude of V times the magnitude of B times the sine of the angle between them times the charge on that particle. So in this case, we plug in our numbers and we see that the magnitude of the magnetic force is 1.6 times 10 to the negative 19 newtons. But we don't know what direction it points in yet. So we need to use the right-hand rule to determine the direction that the resultant vector will point. The way we would do that in this example is we would point our index finger to the left, we would curl our middle finger upward, and then we would extend our thumb and realize in this situation, our thumb is pointing away from us. It's going into the page. that is the negative z direction. The overall force vector would have a magnitude of 1.6 times 10 to the negative 19 newtons, pointing in the negative z direction. We will enter our vector values for vector A and vector B here. So if we take the example where we had our velocity in the negative x direction, that would have a negative 1 for its x component. The magnetic field pointed upwards, so that would have a positive 1 for its y component. And if we wanted to see what these vectors looked like, we could run this code and see that vector A points to the left and vector B points up. So let's go ahead and try to use the right-hand rule for this before we see what direction the resultant vector points in. If we use our right hand and we point our index finger in the negative x direction, pointing to the left, then we can arrange our hand such that we extend our middle finger upward. In this case, when I extend my thumb, it points into the page. It points in the negative z direction, points into the page. So on your paper, you would draw this with a symbol with an X in it, and then you would calculate the magnitude using the formula that we did before. So now I'll go ahead and run the code with the cross product in there, and let's see what we get. So you can see that this simulation has created our resultant vector in the negative z direction. You'll see that this also can calculate the magnitude for us. This only shows the direction of the right-hand rule. And if we take vector A and vector B, multiply their magnitudes times the sine of the angle between them, we will figure out the magnitude of vector C. It points in the negative z direction. Let's try another example. Here we have vector A pointing down, so we would extend our index finger down, and then we have vector B pointing to the right. So we would extend our index finger to the right. When we extend our thumb, we will see that it points out of the page in this example. So this would give us a vector that points in the positive z direction. You'll see in this case that our c vector points in the positive z direction this time, using the right-hand rule. Let's try one more example. Let's say that we have our first vector pointing in the negative z direction and our second vector pointing up. That would look something like this, where our first vector is pointing into the page in the negative z direction, and our second vector is pointing up. In this case, we would point our index finger into the page, and then we would rotate our right hand until we had our middle finger pointed up. So my index finger is into the page, my middle finger is pointing up, and when I extend my thumb, we will see that it points to the right. In this case, our c vector is pointing in the positive x direction. It's pointing to the right. And we could calculate that magnitude using our formula. Of course, these vectors do not have to always equal 1. We could have a particle moving downward with a speed of negative 10 meters per second and a magnetic field that points to the right with a field of 6 Teslas. In this case, our vectors would point down and to the right, and we would use the right-hand rule to determine our direction of our resultant vector. So the first vector points down, the second vector points to the right. In this case, we will see that our resultant vector points out of the page, but the magnitude of our resultant vector is no longer 1. It depends on that formula, so we would have to calculate that, and in this case, our cross product gives us a resultant vector with a magnitude of 60 in the positive z direction.